I'm Filip. I originally did my master's here at Lund, and then I moved to Finland to do my PhD, and then to southern Germany to do my postdoc, which is where I stumbled across this weird thing, Bayesian approaches to numerical analysis. But anyway, since 1 year back, I'm back in Lund. Okay, so let's see what I put in this slide. I did this a couple of weeks ago. I don't really remember. It's good stuff. Okay, yeah. So I'm ripping off of Percy Diakonis, who's kind of introducing this in a way like, so suppose we have some function f of x is equal to some x cosinus hyperbolicus x minus sig pi x. We know the function, right? We can write it down, and it's there. But then, do we really know everything about this function? So, for instance, if we want to integrate it.
Look at me.
Oh, or wait.
You have it there.
Which one?
Don't you have it in front of you, the presentation?
Yes. Yes. Where was I? Oh, yeah. So if we want to integrate this thing, how? Do we have a formula for this? Maybe, maybe not. So typically you will have to resort to numerical integration. And also maybe we just want to find a minimum of this thing. Maybe we can do that, but maybe we cannot. So there are very many cases where we can write down a very simple function, and we want to know something about it, which we will have to resort to numerical computation for. And so what is numerical computations? So if you have a formula for the function, that means you can write a piece of computer code. It evaluates the function up to some machine epsilon, and you get point evaluations. So basically, what the computer sees are just the function evaluated at a bunch of points, and from this it needs to figure out what the answer to your question was. And this is starting to sound a lot like inference. And so let's try this out. So now I'm going to just show you kind of how Bayesian optimization works, bare bones. So I'm going to put some kind of prior on the function. I'm going to put a mean function, which is just a linear interpolance of the function between the endpoints of the interval I'm interested in, because most people can use. You don't have to do. And then I'm obviously going to put some kind of bridge kernel so that my variance tends to 0 at the endpoint because they're basically. And then I'm going to say that my deviations from the mean are actually Gaussian. So this is what our prior looks like. So we've evaluated the endpoints. Now, how do we go about finding the minimum? So we kind of need to figure out where to evaluate the function next. And so what we do need is what's called an acquisition function. So I'm just going to call this f dagger n, the smallest value we've seen so far out of our evaluations, and the corresponding point where we evaluated x dagger n. And there's various ways of sort of designing these acquisition functions, but take, for instance, one way would be to say probability of improvements. So we calculate the probability that our model function is smaller than some value set, which is smaller than the smallest value we've seen so far. And then we just try to maximize the probability of improvement. So we can try to do that. And then we get a new point out. And so what this looks like is this. So again, up top we have the prior. Our current minimum is at the left-hand point. And once we calculate the maximal probability of improvement, we get this, well, that entire function, it's a function, right? So because the probability of improvement depends on where you evaluate. But we see that it's somewhere almost in the middle of it. And so we evaluate that. And now we have a new posterior, of course, and a new acquisition function. And so we can just keep on going. We get a better and better sort of approximation of our function, hopefully. And we keep on exploring. I did this way too many times. Oh, yeah. Yeah, so you do need some kind of termination criteria, of course. I didn't speak about this. I just wanted to show sort of how this progresses over time. And I think my termination criteria for today will be that I should move on with the principle. And also, so that's optimization. It's kind of simple. You just make a basic or like a probabilistic surrogate of your function, and then you sort of incorporate observations and then. And how do we do integration then? Well, okay, so I'm going to put another prior on our integral now. So I put some constant theta, which well, a random variable plus some Wiener process, maybe, yeah. And then of course our data set is just a bunch of point evaluations. So that's typically a numerical analysis that's integration data. You pick a bunch of points, evaluate, and then do linear combination. And what do? We do the same thing, except that well, we use Bayes rules, so we get the posterior of the function, and then we just shift our posterior through this integral operator, and then we get again some mean value for the integrand or for the integral, and we also get a standard deviation. So how does this look? Okay, so here's the prior. It's a probability balance of a prior, to be precise. And this, of course, implies a prior on the value of the integral. Then we should, of course, introduce a bunch of points. So I just picked up a bunch of points. Maybe this is a bunch of Curtis or something like that. And so you can see where the points are, because there's sort of credible bounces go down to 0. So we get these sausages in between the points we have evaluated. And now we get another integral distribution of the integral, and then with the posterior distribution. And is this a reasonable estimate of the integral value? Maybe. Or we could try to increase the points and then see, oh, no, maybe not. I don't really know how to sort of figure out whether the point set you used is sufficient to give a good estimate of your integral, but maybe that's something you can do research into. And so in both of these cases, the function actually looked like this. I should say. I purposefully didn't show you this before because, well, we can plot this, but the computer doesn't see this. It just sees a bunch of points. And okay, yeah, so yeah, okay, so what is numerical analysis? Well, so we have some non-quantity X target, some quantity of interest, Q of X target. So for instance, X could be the integrand, and Q could be the integral operator. And the classical approach is just to approximate X in some space of hypothesis functions, and then fit some function to some data, so typically point evaluations, and then can compute an estimate of X, and then we get shifted through this quantity of interest function. And typically this hypothesis space is just a space of functions for which we can actually solve the problem. So in the case of integration, polynomials, for instance. And so the Bayesian approach is basically just, we can put a prior on the hypothesis space. We can consider many different functions rather than just one. And so maybe it's not too crazy, or maybe it is. I haven't decided yet. I feel more comfortable with this, speaking about this at Bayesian Lund than, for instance, a numerical analysis conference, that's for sure. But so something I've been working on a lot is like, okay, so how do we do this for ODE problems? These are a bit more difficult, so we might maybe do as a vector field at V, maps RD to RD, and then we just say that there's a function y dot, or a function y, which derivative y dot is equal to the vector field evaluated at the switch, and we need some conditions. So that's what an ODE is. And so our unknown quantity is, of course, the actual solution function, which I call y dagger, which is just this flow operator, blah, blah, blah. Doesn't matter. So how do we attack this problem in a basic way? Well, we can, of course, just continue this sort of, put the GP prior on it and go down how the kernel is and so on. But since we have sort of problem in time, maybe we can do things cleverly so that we don't have to invert kernel matrices and so on. And the way to do this cleverly is to just say, oh, my solution is some kind of output of a Gauss-Markov process, so we have some latent X there, which is also a linear stochastic differential equation, and then we can use project the state with some projection matrices EM to get the derivatives of our model for the solution. And so this has the Gauss-Markov property, which means that, how do you say this again? Given now, the future is conditionally independent of the past or something like that. And of course, we can compute the parameters of these sort of transition densities and so on. And so what prior should we choose? That's an open problem, but a kind of reasonable one is just take a linear process and integrate it a bunch of times. Because what happens then is, then we get a model that is kind of a Taylor expansion, except you toss away the remainder term and just replace it with a Brownian motion. So essentially, we're modeling the Taylor remainder. And due to the Gauss-Markov property, this holds basically conditionally if you have the entire vector of derivatives for each point. So it's essentially a polynomial extrapolate. Though you could be clever if you know something about the problem as well. So say, for instance, if our vector field is semi-linear, it has a linear bit and a non-linear bit. Then we can just differentiate it a bunch of times to get, well, the differential equation for the nth derivative. So, of course, the L just stays there, and then we have the nth derivative of the non-linear term, and then we say now the non-linear term is it's just white noise, formal derivative of Wheeler process. Okay, so then we get an integrated Ornstein-Uhlenbeck process into that. And these kind of look like this. So these obviously don't solve any differential equations. So we're making the sort of data bit do a lot of our work for us, for the moment at least. So what is our data? Well, we pick a grid, a bunch of time points, T0 through Tn, in the interval we're interested in solving for. And then we say that maybe the derivative should match the vector field evaluated at this solution at some of these sets of points. And this is typically what the numerical analysis guy would call collocation. But we're doing it kind of stochastically. And so this is our, I don't think this is good. Yeah, well, you can translate it into this X vector, which is important because X is Gauss-Markov, and this is just a bunch of observations with no noise. And so our inference problem is a Gauss-Markov regression problem. A non-linear, but still sufficient. I like that. And so we can kind of solve it. And by kind of, I mean that if it's non-linear, then it gets tricky. But in the linear case, you can do Kalman filtering. In the non-linear case, you can do these kind of approximate Kalman filtering methods, like standard Kalman filtering and so on. You could also try particle filtering. I did that once, but I cheated a bit by putting a nugget in the kind of like root term to make it easy to do proposal distributions and so on. But to do it more cleverly, is something I would like to do as well. And so now let's see what happens. So now we're solving the same differential equation using two different priors. So in the red one, this is the integrated Wheeler process, polynomial extrapolation. I'm not showing the mean estimate, but I'm showing samples inside the credible regions. And then the green one is the integrated Ornstein-Uhlenbeck process. Yeah, what's the solution then? Okay, so the solution, I now added a black line, and you can see that it's very much inside the green one, and of course also inside the red one because it's wide. But as you might have guessed, this was actually a semi-linear problem, which is why the sort of integrated over time process works a lot better. And so the priors matter, and it's kind of an open problem how to figure out good priors for differential equations, because there are some pathologies which I'm probably not going to talk about today, because I thought I'd end here.